So welcome to our Dune Arcana session 4, where in Dune Arcanas, we are going to explore the current Web3 trends and news with on-chain data. So my name's Arga Perste. Today with me, as usual, we've got your Xboxer, and then we got a guest, Michael Silberling, our very own art wizard from Optimism. So
GM.
today,
Fuck nerds.
So today we are going to take you through a ride on what is L2 and what kind of data analytics you can do with L2. Okay, so let's get started. Okay, so at DuneCon, we had the talk with Tomasz Tungas, where he was saying one of the trends in crypto in 2022 is that L2s, namely Arbitrum and Optimism, account for 30 to 40% of all transactions on Ethereum, but consume only 2% of the total gas, cementing their value. That is a wild trend, right? Like 30 to 40% of all transactions and 2% of the total gas only. So looking at this trend in terms of a graph, this is what we will see. So let's actually go to the complementary dashboard. Actually had it open already. Okay, so throughout the session, we'll be using this dashboard to kind of walk through all the data visualizations and like break down on the actual data analytics part. So with the trend that we were just talking about, let's take a look at this graph to the bottom right corner. So here is a graph where on the y-axis we have the time, so the day, and then the y-axis represent the transactions. So it's like the percent of the transactions. So on this graph, we've got the Ethereum number of transactions, and then Optimism transactions and Arbitrum transactions. So here, if we hover over, we can see that the blue bars, which represent the Ethereum mainnet transactions, it's like you can see it's like hovering 70%, 75%, 65%, and then Optimism is 20% is, and Arbitrum like 15%. So we can clearly see the trend that Thomas is talking about, right, through this graph. A lot of transactions happen on the L2 chains, one of them, namely Arbitrum and Optimism. And then, okay, so looking at the gas, we can see that same thing, like on the x-axis, we got the time. So here's like weekly, and then the y-axis represent the percent of gas being consumed. And then here we can see that the percent of gas being consumed by L2s, so like Arbitrum, Optimism, ZK Sync, DYDX, like all those are hovering around actually 2%. Sometimes it can be even lower than that. So clearly this is a large trend that we're seeing. So, but you might be wondering, right, like what exactly are layer twos, and what more things can we do with this layer two data? So we're gonna start with what is L2. So 1 comes before 2. So we're gonna talk about layer 1 first in order to understand layer 2. So layer 1s are not really a concept that's just unique to Ethereum. It actually is like unique across a lot of chains. So Bitcoin, Ethereum, Solana, they're all layer 1s. So these are standalone blockchains themselves. So these are the base layers. So you can think of them like with Ethereum, it has its own like mechanism, consensus mechanism, parameters, its tuning, all the good stuff. And then, so with the layer 2 are a scaling solution that help with increasing the capabilities of L1s by handling transactions off-chain. All right, so let's dig into it a little bit more before we get to like the actual benefit of it. Okay, so why do we need L2s, right? So why do we need this like scaling solution off of L1 chains? So when the demand is high, so think about like if you were in crypto already in 2017 to experience the ICO mania, the crypto kitties, right? And then in 2022, the DeFi summer, and even last year when NFTs were booming, when the demand is high, traffic really gets congested on Ethereum. So as a result, sometimes you're paying $50 to $100 just to like a simple swap. Well, and then you have to wait for a really long time. And that is like a really bad user experience, right? And sometimes it's just like not really affordable. Like people can't pay like $50 to just like swap some tokens. So what we can see also with on-chain data is this. So actually, let's go to the dashboard one more time. Okay, so we're talking about the traffic gets congested, right? So here is a graph that we can see So we have the number of daily transactions in the blue, and then we have the daily median gas in the red orange. And then you can see here that these two are very closely correlated. So when the number of transactions go up, the median gas also go up. So effectively, gas, just think about it as like a transaction fee you have to pay. So when there's a lot of demand, then the gas also jumps up, and you can totally see, right, like 2020 summer-ish, it like really spikes up. So if just to make this like a little bit more concrete in terms of like dollar values, let's take a look at this graph, which is the Ethereum average and median transaction fees. So you can kind of see like on the y-axis, right, the axis actually goes up to like $80. So sometimes it spikes up to even $100 in terms of transaction fees, and that's just really bad, like not affordable. And in contrast to that, if we look at the optimism, which is like an example of layer 2 solution, we can see that the y-axis actually just go up to like single-digit dollars, right? It's like a huge reduction in terms of the fee that you need to pay. So clearly, like we need something like layer 2 to help us solve the scaling problem. Okay, so coming back to our slide. So now we've kind of like saw through data that what the problem is with L1. We now are at the point where like, we really know that we need a scaling solution to help us with a lower transaction fee and a faster transaction time. Okay, so now we've established like why we need L2. Let's talk about like different ways you can, now we've established why we need a scaling solution. Let's talk about different ways you can scale. And then we will like get to the part why we need an L2. Okay, so first off, we can start scale by just scaling the base layer of the blockchain. So like if we want to scale Ethereum, you often hear about sharding. That's one way to do it. And then another way you can scale is through L2s, right? So through L2 scaling is basically you're offloading some of L1's work, so like the execution part of the work to the L2 chains, and then it's built on top of L1s. So it's basically leveraging the security of L1 by anchoring its state into L1. So some of the examples of L2s include Arbitrum, Optimism, Loopring, and ZK Sync. And in addition to that, another way that you might hear to how we can like scale is through sidechains. So sidechains are EVM compatible independent blockchains with their own consensus models and block parameters. So examples of that are Gnosis Chain and Polygon. So I put a star next to Polygon because Polygon itself is also kind of like a layer 1 solution, but they are also a sidechain because they're EVM compatible, and through bridges they can talk to Ethereum. Okay, so coming back to L2s, even within the L2s themselves, there's like different ways that you can achieve scaling. So some of the ways include state channels. So if you're familiar with Bitcoin's Lightning Network, that's one of the example. And then another way is through Plasma. So think about OMG network. And then also you can do it through rollups. So the state channels, Plasmas are out of scope for this current session. We're going to just focus on rollups because that is the preferred L2 scaling solution. And if you want to know more about it, you can go read this post by Vitalik Buterin on a rollup-centric Ethereum roadmap. Okay, so rollups basically bundle or roll up transactions and submit them to L1 in batches. So this is like a good point where we kind of like visit this concept, which is the scalability trilemma, and try to help understand like why we can't just simply, use like our Ethereum base chain to kind of achieve what we wanted to do in terms of scalability. So there's like the scalability trilemma states that there's 3 desirable properties of a blockchain. There's security, there's scalability, and decentralization, right? So think of them as a triangle here. And the trilemma states that the 3 cannot be achieved simultaneously for a blockchain. Only 2 out of the 3. Okay, so if you want to have security and decentralization, then you will not get to scalability, right? And if you have scalability and decentralization, then you cannot get the security. And also, The third scenario, if you want scalability and security, then you are sacrificing decentralization. So this is like, think about it as like your local big bank IT infrastructure. It's pretty scalable, it's pretty secure, but the price that you have to pay, like the trade-off you're making, is that they're running these like big computers, and they are able to just censor you if they want to. So you're sacrificing the decentralization part. But the way with L2, right, the L2 can solve this problem. The L2 can have a higher transaction speed, higher transaction throughputs, and also inherit the security of the underlying L1 it's built on. So effectively with L2, you've got all three. You've got decentralization and security, which are the two properties that we desire in Ethereum, and you've got scalability, right? Okay, so how are L2, or more specifically rollups today, that we're going to talk about, achieve this? So the rollups are the general purpose scaling solutions. So they basically execute transactions outside of L1. So they do all the calculations on the L2 chain themselves. So things are much cheaper. And then after that, they will post transaction data onto L1. So they write the call data, like batch it up to L1. And then so they're using L1 as like a data availability layer, and then they also derive the security from the L1s. So in terms of the flow, the process, it goes like this. So an L2 would execute the data, does all the calculation for the transaction, and then it like takes the data and maybe does some sort of compression. And then it rolls up many transactions into one batch, and then it posts that one batch as part of the call data onto the L1 chain. Okay, so now armed with all this knowledge of like what L2 is, like what rollups is, if we revisit the query that we were just looking at, so if we remember going back here, we were looking at this particular query where we're like, okay, so L2 gas as a percent of ETH gas is like basically 2%. So in order to get this query on the other side, if you look inside of it, there's a bunch of like addresses that we're filtering for. And then if you take Optimism as an example, you can see here, this is an address for Optimism canonical transaction chain address. So basically, when we were talking about like L2s rolling batches of like information into L1, it's basically writing all the data onto like a specific address, and that's how it's posting data onto L1s. And I'm sure Michael will like later on give you more specific examples of like how this is done in action. Okay, so one more thing to mention before we really take a deep dive into this. So in terms of rollups, right, we talked about, so we basically came from like what are L2s, and then different ways you can scale in L2s, and then we like are focusing on the rollups. And then also within rollups, we even have this concept. There's like the zero knowledge rollups and the optimistic rollups, right? So what are the differences and the similarities? So both rollups, the ZK rollup and optimistic rollup, they roll up transactions in a single batch and post the transaction data to L1, but they differ primarily on how this transaction data is posted and how the data is verified. Okay, so for the ZK rollup, they use validity proof. What that means is that they run the computations off-chain and calculate a zero-knowledge proof, and then post the data along with this proof onto L1. And generally speaking, it's mostly application specific. Whereas for optimistic rollup, right, it uses a fault proof. So the transactions are assumed to be valid, so very optimistic, and then can be challenged. So these transactions that are posted can be challenged if necessary. So generally, there's a 7-day period window where when the transactions are posted into L1, you can challenge the validity, and then only the optimistic rollup will only run the computations on chain when fault is suspected. So if someone like flags, hey, something is wrong with this, then only then we'll run the computations on chain. And then generally, it's largely generalizable. Actually, correction, with the validity proof for ZK, it's only the proof that's being transmitted to the L1 chain. Okay, so that was a lot to digest. So just to recap, we went from what is L2 to what is rollup, to specifically we talked about optimistic rollups. So for the rest of the session, we're going to use optimism, so a type of optimistic rollup, as an example to help us make a deeper dive into how L2 rolls up data into L1, how to look at L2 gas fees, and also call data compressions. So now I will welcome Michael to be on the stage to take us through the rest of the journey.
Awesome. Yeah, I can take over the screen. Yeah, thanks. That was a great, yeah, definitely like a good primer on everything we do. Yeah, so as mentioned at the top, I'm Michael, data analyst at OP Labs, contributors to Optimism and the Optimism Collective. So yeah, I just want to give kind of concrete examples for everything that we just went through. What this looks like on chain if you're looking through Etherscan or looking through transaction tables in Dune, how to pull out what's actually happening. So a cool thing it's like a whole scope of layer 2 data. You could look at like what's happening at the application layer, what users are doing. That stuff is all pretty similar. If you're looking at like a DEX on layer 1 versus DEX on layer 2, it'd be fairly similar. I can share my screen, ramble. Cool. Yeah. So yeah, with that context, I wanted to just focus here on what things are kind of unique about layer 2s, specifically about data being sent between layers, how gas fees are calculated, some of the efforts going on to eventually kind of lower these fees, and everything throughout there. So yeah, it's kind of like similar to what we mentioned before. Yeah, how we send it from L2 to L1, how our fees are calculated. But like everything moving quickly, probably a lot of the exact detail here will be outdated very shortly. As new protocol versions are coming out, as new EIPs are going through. But like general of how these things work will still and hopefully help with understanding how to adapt and adjust to some of these protocol changes that will come through. And actually, I'm going to share my screen in a different mode, so maybe easier. There we go. Hold on. Technical difficulties earlier were my problem. Okay, now we got it. Cool. So to start here, we'll walk through kind of the life cycle of an L2 transaction. So if you use Optimism, use any other kind of layer 2, you just connect your wallet, send a transaction like you would anywhere else. Example here is a NFT trade on Quixotic, now known as Quix. So general kind of transaction, ETH transfer, ERC-721 transferred. So what you'll see in this transaction, if you scroll down to the very bottom, there's this like big input data thing, kind of tells you all the information about the transaction. It's like what a user sending a transaction has sent to the EVM to then get all this computation, all the gas we talked about, how all that happens. So this is like the very nice structured version that Etherscan will do. But at the rawest form, it's like this huge long byte string. Using Dune or any other kind of chain checker, you'll see like the data field or input data field. That's just this whole byte string. This is known as call data. So that's important to know, kind of go throughout. But this is the information that when we say an L2 sends data to L1, it's this call data, like showing what the user sent to the L2 that's actually being sent. So you also see in this transaction, after some time's passed, this transaction was sent down to L1. Ether's a nice way of linking those things together, showing you for this transaction I sent on L2, where can I see where it was submitted on L1? And then this call data here will be relevant for that. So in a batch, like you mentioned, like if you click on any of these like transaction batch index here, you'll see all the other L2 transactions that were included in this L1 batch. So this one specifically is from December of last year. There are about 140 transactions included in the batch. And we'll see how this all kind of comes through to L1. And just for kind of like closing up context here, before we go into what the L1 transaction looks like, these batches happen usually like every few minutes. Definitely varies by different kind of protocol design or any kind of that may happen. So you can see recently, Arbitrum's time between batches increased a little bit. Optimism's time between batches decreased a little bit beyond that, but historically they kind of tracked pretty closely, about a few minutes between batches. But cool. So kind of going back up transactions, then going down to L1, what's actually happening. So if we follow the link from the L2 transaction down to what its submission was, that's this transaction. So using L1 Etherscan here, you'll see like an event here with all the information about the batch, or just the rough information to link actions back to which L2 batch they were in. So you can see like what the starting number was of previous total elements, like how many transactions were included up until this batch. This batch was 140 elements, and you could link things up through this. And then you look through in this transaction, similarly, scroll all the way down to this input data. You see this append sequencer batch call, and then like a whole bunch of zeros. Like it goes, if I actually did extend all the way, it would go like under the ground, like a whole bunch of data there. So this data. This is as of December last year, before a bunch of other upgrades happened. This is the input data we showed from our L2 transaction, all just appended together with some other data in it too, into the L1 transaction. You can take your call data for your L2 transaction, like Control F, find it on layer 1. So we say like layer 2 data is sent to layer 1. Like this is it actually happening. Like your data just gets taken and sent along with all the other transactions in this batch. This is expensive, as you can see. Like taking all this data, appending it together, kind of long forever. And the more data it's sent to L1, the more expensive it is to send. So we'll jump into a little bit of how this fee model works and why that is. So backing up first, what is gas? We referenced a little bit earlier. Some definitions from the Ethereum site. Just you can think of it. If you think of like your gas fee, it's how much you pay to conduct a transaction on Ethereum. The Ethereum website defines this as a unit measuring the amount of computational effort to execute specific operations on Ethereum. So if you think about, anytime you've done like any kind of data analysis looking at transaction fees, it's just how much gas your transaction uses, which we'll get into how to calculate that, times the price of gas at that moment, whether it's like 100 gwei, 50 gwei, 20 gwei. And what's important to know here as well, the part of gas that really influences rollups is like what the cost of gas is in the call data, or in this like input portion. So if you, so I'll go back up here, look at all these bytes, or look at this whole string, you can break up into bytes. So like this, if you look at the L2 call data here, like 6 zeros the first byte, F4 second byte, all the way through. Each of those bytes have a cost to send to Ethereum. So in like the Ethereum yellow paper, you'll see it's 4 times the number of 0 bytes plus 16 times the number of non-zero bytes. That's like your total call data gas. And that is, because if you hear call data, that's like the, one of the big costs for rollups today. And we'll show that in a nice visual segment later too. So going back to this L1 batch submission, now kind of understanding like each of these bytes has a cost associated with it. The 0 bytes have a cost, the non-zero bytes have a cost. You might look at this and be like, it's a lot of information. How do we kind of make this smaller? Or how can we make this cheaper? So that's where call data compression comes in. Take all the data and just make it smaller. Meme kind of works. But you can see a link at the bottom here. There's you can search like some blog posts that we posted about doing this call data compression. And so now, like as of now, both Optimism and Arbitrum, to my knowledge, do call data compression. So good source of cost savings there. And so what that looks like, so think of before, this whole huge array of a bunch of zeros here. With compression, like, let's look at all the zeros going away. It's like very satisfying seeing all the, looking at numbers changing. But actually looking at impact here, so this is like a screenshot of a Dune query and what the result is. But you can read, as you can see here, there's the canonical transaction chain is a contract on L1 that transaction batches are currently sent to. So this query is doing, like this segment of it, you can see, taking transactions before compression was launched, so just the month of February this year, compared versus the month after compression was launched, and then just for comparison, showing what the last 30 days look like here as well. So what you can just look at is like how much, what the L1 footprint is of an L2 transaction. So how much gas on L1 the transaction's using. Before compression, this gray bar is like higher, about like 4 to 6K gas per transaction. After compression, you saw it drop to about 3. And and it definitely fluctuates by transaction type, compression algorithms, things like that. And how we measure this over time. So there's this thing called a call data compression ratio. How do I explain this? So, as you can see up top in this query, extracting bytes in SQL is kind of messy. So just copy and paste this stuff here. This is just taking from our data string. So this is from taking a query from a transactions table, from this data string, do this mess to get how many non-zero bytes there are, multiply by 16, whole other mess to get the number of 0 bytes, multiply it by 4, you'll get the amount of call data gas. So you can just measure here the amount of call data used on L2 versus the amount of call data used in layer 1 batch submissions, and just calculate the ratio of how much call data is actually used on L2 versus how much is actually paid out on L1. And so it's relevant there to know is just before call data compression, you could do this find replace to find your transactions on L1. Now, since it's compressed, it's all done at the node level. You can't do it on Etherscan anymore because it's all just compressed and not human readable bytes. But for context there of how layer 2s have so far done some work to try to reduce fees. And why it matters, why even doing all this call data compression matters. So if think about how or going into how L2 transaction fees are calculated, what makes them magically cheaper. So transaction fees on layer 2, and this is kind of specific to Optimism. I'll show the Arbitrum transaction fee calculation when we get to it, but I'm personally more familiar with Optimism, so I'll focus on that. So transaction fees on layer 2 are kind of split up into 2 different types of fees. So one of them we call the L1 data fee, which is kind of what I just went through, the cost to take this input data on L2, submit it down to L1. And then this L2 execution fee, which is just the cost for running a transaction on layer 2. Like mentioned before, the execution is off chain, so that's where that gets way cheaper. So going deeper into the L1 data fee, decomposing it a little bit, you'll see that in Dune, you'll see that there's a field called L1 gas used. So it's just a calculation of how much gas is being used in this data sending down to L1. It's calculated there, so it's nice. That times the L1 gas price. So since that is data that's being sent to L1, the L2 has to pay the L1 gas price for that. And then we mentioned before, how much gas that is a function of how much of the input data is there. And then the L2 execution fee kind of seems straightforward as well, just how much gas is being used on L2, and then what that gas price of layer 2 gas is. So breaking it down more, what it looks like in Dune, kind of mentioned already. But for Optimism, this L1 gas used, L1 gas price is bundled up to this L1 fee field. So you can just take that and then add the traditional gas used, gas price is L2 gas used, L2 gas price. You can get into, I'll get into later, how using that L2 gas used can let you do some pretty interesting things. And then on Arbitrum, there's an effective gas price times a gas used field. There's a separate gas accounting there. But both of these things, get you to the total transaction fee on L2. All right. So just decomposing this a little further, maybe touched on this a little bit already, but when we talk about L1 fees, what's actually happening under the hood? So we already talked about gas used, gas price. There is a fee scaler in the Optimism fee calculation, which historically, when Optimism first launched, that fee scaler was set to 1.5. So there was an extra 50% margin charge on top of all transaction fees that was earmarked to fund public goods. Since then, as compressions come through with the EVM equivalence upgrade, other costs to submit to L1 have decreased a little bit. That scaler's come down as well. So the scaler is currently 1. So it doesn't really impact gas price calculations now, but here's the full decomposed thing. And you can even decompose L1 gas used further into call data plus overhead gas plus non-call data gas. It just is a continuous nesting doll of gas to get to the actual final number. And then L2 execution fee, we've talked about a few times already, but the L1, L2 gas price is Usually like the floor is like 0.001 Gwei. Rarely, I mean, it will raise above that, but usually not much. So currently this L2 fee, as we'll see, is kind of negligible. Cool. So here's kind of a good visualization of that. So this is a query you'll see on the big master dashboard. Yeah, so this is taking, like decomposing this transaction on Optimism, taking like of the total transaction fee, what share of it is due to the L2 fee, what share of it is due to the gas using the gas price. So there's some like random kind of variability, but over the long run, you'll see that the total share of the L1 fee for an Optimism transaction is like 90 to 99%. So that's, yeah, pretty large. And where we say like the L2 costs so far are kind of negligible. So when we talk about things like call data compression or any other kind of strategies, yeah, like at least in my mind, this like low hanging fruit here is of how to lower fees more is like take the L1 fee portion and try to reduce that as much as we can. Cool. Yeah, so gas fees are kind of low today. Like gas prices on L1 are low. So you look at like doing a trade on an L2 now, still fairly cheap. Like just average yesterday, Arbitrum was about 9 cents for Uniswap trade. Optimism about 16 cents. But if you want to keep reducing fees, where's the focus? Clicked off the screen. There we go. So yeah, I mentioned before, my opinion, lowest hanging fruit is try to reduce the L1 portion. So there's a few ways we've kind of seen these fees get reduced so far. So one is just in general, increased transaction volume in the sense of if you think about submitting batches to L1, the larger a batch is with each transaction batch submission now that is executing a contract on L1. So beyond the call data you send, there is some fixed costs for just like executing that transaction. So when L2 fees are calculated, that cost called like overhead cost is kind of amortized across all the transactions in the batch. So you see here on the left is just a sample of Optimism transactions where the X is how many transactions are in the batch. The Y is how much gas is amortized over, or how much overhead gas is used per transaction. And it's pretty kind of a steep decline. Yeah, just more transactions that gas cost goes down. And the right kind of talked about already. You can compress the call data, probably continuously get better at those algorithms and make that L1 share smaller. So these are things that have kind of happened in the past, been tried in the past, continually worked on. Yeah. Other thing that's kind of coming up recently is how we reduce the L1 footprint. So this is one that's kind of still getting up to speed on as well. But just to kind of mention here, there's a push out for EIP 4844, which is saying rather than posting, my understanding of it, rather than posting all the transaction data to L1, you post some cryptographic commitment to L1, pointing to where the data is, and the data is stored in nodes temporarily, then eventually pruned. Just ways to, it's in my mind, I was thinking like, how do we do all this optimization stuff like up here? And then another solution to all of this is like, well, what if we just kind of work on the L1? So the CIP has kind of been a combined effort between OP Labs, Coinbase, Ethereum Foundation, a few other individual contributors as well. But yeah, definitely a whole rabbit hole deep dive to go into. Okay, back to today. So last thing to touch on, which I think is like very cool about the Optimism design and just kind of communicating the L2 value prop in general, is when I showed the gas used field on Optimism before, which is the L2 gas used field. What's a cool property of the Optimism design is that L2 gas used field is equal to how much gas that same transaction would use on L1. So example, like an ETH transfer is 21,000 gas on L1. It's also 21,000 L2 gas on L2. So you can do the same thing with like a Uniswap trade or any other L2 app. So that's pretty cool. And then we have the L1 gas price as a field passed in by an oracle. So there's this kind of cool thing you can do to calculate, if you want to do hypothetically say how much ETH has been saved by L2s, or how much cheaper is this transaction on L2 than layer 1. You have this like pretty simple calculation to do. So similar to like layer 1, you just do gas use times gas price. Here we can do L2 gas used times the L1 gas price, and that gives us, for a given L2 transaction, how much cheaper is it on layer 1. And we have a table dashboard to show what it looks like in action as well. And you can go the other direction as well. Definitely some more assumptions there, but I think a cool value prop, you can use how much call data an L1 transaction uses to kind of simulate, like, this L1 app, this DAO vote, this whatever, how much that costs on layer 2 is a cool. It's been, I think, beneficial so far for kind of communicating what a value prop is for an app to migrate some of its usage to layer 2. Cool. So like I mentioned, these things are probably easier shown live. So I could jump over to, cool, it does work. This dashboard. Scroll. Yeah. So I'll jump on into this table now. So this is kind of talking about before. Using all the information of a transaction on layer 2, simulate how much layer 1. So see, I can jump into a little bit here. Maybe I'll talk about first. So joined, like, what type of transaction it is. So here is like a staking transaction on Pika. Where's another good one? Chain Oracle, some token approvals, doing perp stuff. So if I wanted to, so like I mentioned before, these are just transactions coming from the Optimism transactions table. So if I want to calculate what is the transaction fee in ETH, the L1 fee, add the gas used, gas price, adjust it for
Michael,
ETH decimals.
real quick, zoom in your screen a bit and maybe scroll a bit slower. The stream is not catching up to your scrolling speed.
Okay.
That's better. Thank you.
Cool. So in general, okay, I'll try to stop scrolling. I scroll a lot. So if I want to calculate what the layer 2 gas fee is, showed before, you take yield, which aggregates all this other stuff together. Add that to gas used, L2 gas price, decimal adjusted. There's your ETH fee. And similarly, what I mentioned, I'll take the same exact transaction, find out what it costs on L1, just this field, but instead of doing all this L2 gas price, call data fee, addition, you take that actual used, multiply by the L1 gas price, and do what that fee would be on L1. And then from there, it's just like a building block to do kinds of things, try to, like, not scroll fast. Let's do all kinds of things like how many times cheaper is it? Or like what's the share of the fee that's L1 versus 2? How many times cheaper is it? All these kinds of things. So I think it's like a kind of a cool example here too of how some apps are built. These savings be like way, way higher. So we'll find out it's actually mapped here well. Maybe I'll type in a few. So one example here. So Uniswap trade, that's migrated from L1 to L2. Take this transaction here. This transaction cost in Optimism is 18 cents. Same transaction would be 538 on L1. That's about 30 times cheaper. Probably likely a fair price contract for L1. Go to some of these L2 native apps, something like Lyra, which is a protocol. This transaction here, like method's not decoded, but cost 11 cents on Optimism would be $42 on layer 1, like some over 300 times cheaper. I think an interesting example there of, I guess, contribute to this is that this app uses so much L2 to Uniswap trade if you compared those. So I think a good example here of just some types of that, because of like how much they do behind the scenes, are just like would not be feasible on L1. Like imagine that today's gas price is paying $40 for a transaction, but on layer 2, because of just how things are constructed, it's definitely a much more manageable 11-cent transaction fee today. And there's also this other dashboard here, which we have kind of mentioned a lot more assumptions going on, but kind of going the opposite way of taking any L1 transaction hash and saying alignment's a little off, but what it costs on layer 2, on layer 1 today, what it would cost on layer 2 projected. The call showed earlier is a big contributor to that, and then make that case as well. So I can go into this if we have time, but definitely want to make sure we have time for Q&A and other things. But in general, if you're interested in layer 2s and all this kind of stuff, just throw out some other interesting ways to get involved. So we have an analytics channel in the Optimism Discord. Other apps and other L2s definitely have very active analytics communities as well. And then, any kind of spells or cool dashboards for any layer 2 would be cool. Listed a few ideas here, whether it's like NFT-wide stuff, bridges we didn't touch on, but bridges are a whole other crazy sector, like probably more complicated than DEXs. That's like definitely hard to wrangle. And there's been some things about 4844, any other ideas from today. And then I was watching some of the DevCon talks yesterday, and it's definitely very, very hyped, very exciting. So definitely recommend to watch some of those if you haven't already. But yeah, that's end of my long-winded ramble.
That was a great ramble. Thank you.
Yeah,
that was amazing.
I'm
very
ahead.
content, very juicy content. Yeah,
yeah.
Sorry,
There's a lot of stuff being thrown out really quick. Yeah.
Yeah, I thought it was gonna be a roller coaster ride, and it was a roller coaster ride. A lot of stuff.
All right. Yeah, I certainly learned something. Maybe before the Q&A, a quick cheeky questions. Are L2 devs getting lazy because they have so much, because there's not as big of an incentive to kind of save on gas?
Oh yeah. Not sure. I definitely can't speak to that, but I do know that there's some. Yeah, and who knows there? But I can just as some examples. There's been some apps that we've noticed that kind of optimize their contracts for how an L2 calculates transaction fees. So there was a call data compression or a DEX that did call data compression at the app level before Optimism had it at the protocol level. So they were getting I think at a time where transactions were $1 or something, they were doing transactions for a few cents. And Aave v3, I believe, also did something similar. I think they announced this where they designed their contracts in a way that used less call data, so try to optimize for layer 2 fees. So that's definitely been a pattern that's happened. I think you see it with some some trading bots will do some similar things as well with trying to optimize their call data. I don't know. It's hard to say. Will it be similar to building a contract on layer 1 a few years ago? You're who cares about gas fees? And then all of a sudden, oh man, your gas price matters, or how much your gas uses matters. It's still early to say, but I don't know. I can just speculate myself.
Yeah. Okay. So we will just assume they're not getting lazy.
Yeah.
I mean, they're making the best they're making efficient use of their time. It's why optimize gas costs if you can in the end you'll save 5 cents on a transaction. Maybe that's not really the way to do this. All right, there was a couple of questions throughout the stream. We have this beautiful question from all the way at the start, which was, why is the median gas between December 2017 and March 21 so different, even though the daily transactions are roughly similar? I think this was in Jackie's presentation part. So maybe, Jackie, if you can share your screen and we can take a look at that, and maybe we can make sense of it.
Yeah.
So your screen is back online.
Thank you. I think we were talking about this graph. I will make it bigger. This big enough?
Scroll down a bit. So the daily transactions and the median gas. I
have a speculation guess. So I wonder. So I think that you'll see with layer 1 transactions, especially recently, they kind of are capping around 1 million or 1.2 million per day. Even if you look at just the amount of gas used on Ethereum, you'll see it's pretty much at its cap now. So essentially there's more demand for gas than there is supply for it. So long way of saying that my interpretation is gas price is more of a measure of excess demand versus current transaction volume. That's just my kind of mental framework for it. If there's more competition to get into a block, gas price would go up.
Yeah. I subscribe to that notion too. It's just like there's only a certain amount of block space, and if we go over that, like we can only fit so many transactions in a day into the like blocks. So if there's like excess demand, the median gas price can still go higher. So it's like a function of excess block space demand, pretty much.
Yeah, and there's a cool property too about like layer 2s. You'll see in that shared dashboard as well. But there have been a few days so far, even though the transactions are still like 20 or some small percentage of layer 1. There have been days where the layer 2 gas on Optimism is greater than the layer 1 gas used on Ethereum. Just kind of a sense of like there being just like way more, like I don't know what the limit is, but just like more space for gas usage like via layer 2s than just the same limit on layer 1. Probably said that very confusing, but yeah.
Yeah, no, like the total block space grows pretty much.
Right.
All right, then there was so when Jackie was explaining ZK rollups and optimistic rollups, there was a comment. Only optimistic rollups post data onto L1. ZK rollups only post proofs, and that is correct. I think Jackie misspoke there, or
Sorry.
yeah, like to be clear,
It's all confusing.
Yeah, yeah, it really is. Optimistic rollups actually post their whole call data onto the L1. ZK rollups actually just post proofs, just to make that very clear. Then, all right, what else do we have? Yeah, I discussed with someone in the chat. Maybe we can bring up in Michael's part of the presentation, there is L1 gas per L2 transaction chart.
Yeah, it's maybe not worded well, but I was trying to show there is, yeah, we can go to that.
This is
where is it? Oh, I think it's very bottom left. Yeah, very bottom left. So that's saying, yeah, maybe it could be like labeled that like orange. I guess all of them have the same color scheme, but that one,
Yep.
yeah.
This one, okay.
So what it's trying to show is for a given transaction on layer 2, how much gas is it actually using on layer 1? So the batch size in the transaction chain is like how many transactions are in that batch. So yeah, so it's just getting at like, yeah, for a given layer 2 transaction, what's the size of its layer 1 footprint? So like,
yeah,
in a
and
sense, like, yeah. Like,
yeah,
like
he was asking like, isn't this a lot? And you need to account for the currency. So this is actual gas computation units, and usual like a usual like ERC20 transfer. So if I send Jackie 100 DAI, then I will pay 21,000 gas computation units. So if you think about how complex some of the transactions are on Optimism, as we saw later in Michael's presentation with like Lyra spending a shitload of gas, which basically translates to they're doing a lot of computation on chain. Then like 2.5k gas is like, that's pennies. So it's like 1/10, not even 1/10 of like it's 1/10 of a usual ERC20 transfer. So it's like 70 cents or something. So it's a really good price. Of course, depending on how expensive L1 gas is at the moment, because that's a like outside influence. But still, like if you pay like 2.5k gas, even if the gas price is like 100 gwei, you're still like, it's pretty cheap.
Yeah, definitely. When I started looking at layer 2s was the first time I really ever thought about things in gas units. I forget that I'm now just like used to gas units, and otherwise it's just like a random number that means nothing.
Yep. Yeah, it's always hard to get into these details. Like if you are all the way zoomed in and like inside of these details, it's sometimes hard to explain this actually. Then we have Rob asking, do we have any data stats that are visible on-chain for the fraud-proof and dispute flows? Or do they just happen on mainnet? Yeah, so I'd say right now, like fault proofs are not live in production. There is a repo called Canon that was like, it's developed by like GeoHot, who's like the iPhone jailbreak guy. Now found like Comma AI. So he built like the first implementation of a fault proof for Optimism, or what an Optimism fault proof could look like. Getting those things in production are definitely necessary steps. L2Beat has a good, kind of like rundown of all the different kind of
security properties of different rollups today.
So to answer that question, we don't we don't really. Okay.
Right. Short answer, no. Yeah. But they will happen on mainnet.
But where are they currently conducted? Within the Optimism validator network thing?
Yeah. So currently there's only one sequencer. So it's like Optimism sequencing the transactions. But yeah, once there is like and this is just my understanding of things, like definitely not a protocol engineer, but my understanding is like once these like sequencer sets more decentralized, then you need that mechanism.
Yep. Yeah, makes sense. Then we have another one, which is, can you comment on the utility of layer 2s after mainnet includes sharding?
My understanding, things get cheaper again. As layer 1 gets cheaper, layer 2 gets cheaper. If you think of, I guess regardless of any future upgrades, but I think like if things stay as the status quo today, like my kind of framework understanding, if things stay the status quo they are today, as far as like how a layer 2 transaction fee is like comprised of, if sharding makes the layer 1 fee decrease, then it should also make the layer 2 fee decrease.
Okay, but I think the person who's asking this question is asking, do I even need Optimism if there's like native sharding within Ethereum? I like, of course we do.
How much do you want to pay? Yeah, depends how. I mean, I definitely subscribe to the idea that people always want things cheaper if they can. But yeah, I guess we'll see what happens in the future.
Makes sense. I don't even know what this is. Maybe we talk a bit about Immutable X. Does anybody have like something smart to say about this?
Other people probably do.
We're like data people. We're not protocol people. All right, and our favorite data analyst Hildoby asked. Oh man, I can't.
Yeah, I can see it inside. Glad you asked.
What excites you most?
Yeah. Let's see. Think how I put this all together. I think it's like excited about just generally like lowering the barrier to do things, and like all these different. So like one side is like lowering the barrier in terms of transaction fees, like how many more use cases that can enable. And I kind of like, I think a lot of these things are doing at the layer 2 level, and like other things to come to, or just like creating some base primitive that people can build on top of. So there's like today that's like lower transaction fees. What was like announced at Bogota, like DevCon yesterday, is this like OP stack idea. We're kind of like embracing that. People can like take the OP code base, change some modules, like whether they want to post data somewhere else or make execution operate somewhat differently, and build like crazy games and all these kinds of things. So I think it's like just more excited of just kind of like opening the surface area of what's possible, and seeing what could be built on top of that. So very vague answer, I guess, but I think watch some of the DevCon talks and you'll get hyped.
Yes. I talked to Chuchin a bunch about this in Berlin, and I already like things just click in place if you think about it long enough. It's very exciting. So very very much looking forward to what people build on top of the stack, and like really the modularity of it is very interesting. All right, so I think we're on time. So thank you very much for again visiting a Dune hosted podcast, Michael. Always a pleasure to see you, and also oh yeah,
there you go.
Do we actually send out mugs for this? I think we should. But all right, thanks for coming on.
Thank you.
Thanks for having me.
Thanks for the great presentation, both Jackie and Michael, and we'll see everyone again in 2 weeks. Do we have a topic, Jackie?
Not yet. We are waiting for what Web3 stuff will happen in a week. So
okay.
It's like a whole
if anyone wants to be a guest, slide into Jackie's DMs.
Yes.
And we'll figure that out. Yes. All right. Thank you, everyone. Bye bye.